Welcome to the CCOM Data Visualization Lab. Here we study how we can apply interactive data visualization to support ocean mapping and ocean technologies in general. We do everything from interactive touchscreens to 3D stereoscopic monitors, weather visualization, ocean mammal tracking. We do a lot of virtual reality and augmented reality. We have a ship simulator that we built. And then we also have this large format tile display that we use for collaborative visualization and outreach events and presentations. One of my research interests is how we can use augmented reality technology to increase safety of navigation. Augmented reality is a technology that superimposes a digital content on top of your real-world view. So this would have a great implication for mariners because they don't have to take their eyes off of the water to get navigational information, and keeping one's eyes on the water is the #1 factor in avoiding ship collisions. So this is a Microsoft HoloLens. It's a first generation AR device. We got one of these and we wrote our own augmented reality navigation software for it, which is what you're seeing in the background here. But one of the big problems we ran into is it's just not bright enough to use outside during the day. Another shortcoming we found with these first generation units is they have extremely narrow fields of view. So you're only getting digital content in the very center of your vision. And you can imagine that that cuts down on the situational awareness of the user. And we wanted to do an experiment to kind of figure out what is the strength of that effect, how much of a limitation is it, and what kind of field of view do we need out of future AR devices for them to be useful for ship navigation. To do that, we created a ship simulator using virtual reality, and in there we're able to play around with all kinds of AR overlays at the full 120 field of view of the virtual reality. Our ship simulator allows us to conduct studies in any environment or weather condition without the expense of ship time or the danger of giving undergrads control of a real boat. Here we are able to simulate a wide range of potential AR devices and try out different AR overlay designs without wasting time dealing with hardware hassles such as registration or brightness issues. We found that some navigational data, such as track lines, feature locations, and compass bearings, work great in heads-up displays, while other data types, such as surface currents and bathymetry, are just not very useful when displayed in a first-person perspective. We conducted a human factors study to determine the effects of restricted field of view on the usefulness of augmented reality for ship navigation. Study participants were tasked with piloting the virtual boat from buoy to buoy using both AR overlays and a traditional electronic chart display to find the target buoys and navigate between them. By using an eye tracker inside of the VR headset, we were able to measure how quickly participants located targets, how many times they took their eyes off of the water to check the electronic chart, and how much attention they paid to surrounding ship traffic and kayakers.
When no augmented reality was provided, which is the red line here, it took participants much longer to get their eyes on the target. We also saw that for wider fields of view, targets were generally acquired faster. Augmented reality overlays were very effective at presenting navigational waypoints while keeping mariners' eyes on the water. When there was no augmented reality overlays, participants looked at the ECDIS map over twice as often and took their eyes off the water for over twice as long. Interestingly, we found that field of view didn't really have an effect on this, so that tells us that even restricted field of view augmented reality devices can greatly increase marine navigation safety.
So now we're moving beyond simulating augmented reality and virtual reality, and we're trying to create a true augmented reality prototype that we can use both here in the lab and out on our boat. And we're doing that using these Nreal AR glasses. They're much less obtrusive than a HoloLens or any big headset that we have to strap on. They're very lightweight, and they accomplish that by being run off of a cell phone. So this is where the battery and the computation are offloaded to, and then I can just stick that in my pocket. And then what we do is we have the visuals from our simulation up here on our tile display, and then I can get actual AR overlay imagery within my headset. And then we should be able to also take this out on the boat, and we can use it there and just hook into the boat's navigational and positioning system. These are color LiDAR scans of the bridges and shorelines along the lower 230 miles of the Mississippi River. They were collected to help support NOAA's precision navigation efforts. This data can be extremely useful for navigation, but first it must be cleaned to remove lots of noise and extraneous objects that were captured during the scan. To help with this process, we have developed a virtual reality point cloud cleaning tool, which has been experimentally shown to be significantly faster than existing desktop applications. Once it has been cleaned, this data can then be integrated into electronic chart displays and portable pilot units to provide highly detailed information about shoreline infrastructure and potential hazards to navigation. It can also be used to calculate real-time vessel clearances and provide helpful visual reference. For example, this is our web-based visualization interface that streams the shoreline LiDAR data and NOAA-UNH tiles directly to your web browser. We also use these LiDAR scans in our precision navigation simulations. Here, we download real-time air gap sensor data directly from the NOAA Ports website and use it to dynamically set the water level in the simulation. By loading a 3D model of your ship and entering its draft, we can then calculate and display real-time clearances to the bridge span and pilings. Nautical textual information, such as notice to mariners, sailing directions, and coast pilot, help mariners improve situational awareness while navigating in unfamiliar waters. As we evolve from raster charts to electronic charts, we also need to digitize this textual information. Until now, the best anyone has done to digitize this text has been adding links to PDF versions of the information or georeferencing paragraphs from the text. Our research efforts here at CCOM to digitize this text has mostly focused on ways to restructure the data to be more user-friendly by breaking down the text for categorization of specific components that are relative to different tasks and needs. These efforts are done in conjunction with the IHO S100 standardization process. Our joint work with the IHO allows the Center to assist in setting standards for nautical text and to become early testers of S100 standards that highlight what works and what might still be lacking. The Center has been using the Coast Pilot as its primary source for textual information and has shown benefits of having it separated into categories and linked together. For example, we have developed proof-of-concept portrayals that integrate textual surface current information directly with S111 modeled data. This allows us to show the usefulness of this textual information to fill gaps where S111 data has not been modeled. We also digitized harbor infrastructure features that are described in the Mississippi River Coast Pilot text into new S131 IHO standard, which can be plotted, filtered, and viewed in advanced charting and piloting interfaces, such as our web-based visualization that's shown here. We have also produced the first valid sample of standardized data for S127 Marine Traffic Services that has been tested in a CARIS system. These results of our ongoing efforts demonstrate the many ways that digitizing nautical textual information can add value to and increase the capabilities of the chart of the future.